I think it is now okay. Yes. All right, so that should work. Okay, everybody, it's a great pleasure to be here. And I will tell you a little bit about something different, change of pace compared to what we have discussed the past few days. New Physics in the Cosmos is the title of my talk, but a more relevant subtitle would be Cosmology at the Edges. So let me tell you a little bit about what I mean by that. So cosmology at the edges. I'm interested in probing the contents of the universe, how much we have of dark matter, dark energy, and the little bit that's us, on the largest non-expanding scales around galaxy clusters. Okay, so that's going to be the cartoon I'm going to be showing and discussing. So what we have is at the center a relaxed, virialized galaxy cluster just sitting there. And then, of course, you have matter still accreting on it. And eventually you go far away from the cluster, you hit the Hubble flow, right? And the universe is expanding again. Somewhere in between, there should be a boundary where you transition from expansion to inflow. And that is the turnaround radius, the largest non-expanding scale. And my argument is that there, you're particularly sensitive to the cosmological parameters, especially dark energy. And that I'm going to try to convince you about that. There is a single message of this talk, and that is, I will come back to it again and again, turnaround density probes cosmology. And by the end of the talk, I'm hoping to have informed you about what turnaround density is and convince you that it indeed probes cosmology. Okay, so now that I have your attention and still early in the talk, let me start with a recap of my talk. Okay, the cartoon again. So you have the galaxy cluster, you have the infall around it, you have the expansion of the universe very far away from it, and that is the turnaround radius. Okay, and if you take all of the matter inside that turnaround radius, and you divide by the volume of that sphere that is defined by the turnaround radius, you get the turnaround density. So what about that turnaround density? The average matter density within that turnaround radius, which is the turnaround density, is universal. So it is a quantity that is the same for all clusters at a given redshift, given the cosmology, independently of their mass or their assembly history. Right? It's the thing. You look at them at the turnaround radius, and if you add up all the matter inside, you get a value for the average density. It does depend on redshift and cosmology. This is why it's useful for probing cosmology. And this holds true, the statements that I just made, both for spherical collapse and in realistic simulated clusters. As a cosmological probe, it has some unique virtues. I will come back to those. It's sensitive to the cosmological constant, dark energy. It is local. That is, it measures dark energy in that blob of space-time rather than the universe as a whole, which is rather unique for a probe of dark energy. And it measures it today in the local universe and on cluster scales. And for all these reasons, we should observe it. Okay, and that's how I will end my talk. Okay, so that's the recap. Let me start with the stories. I will try to err more on the side of more stories than more equations. Okay, so the team, it's a little bit more nuanced than that, but really that's the team. It's Yorgos Korchidis. And I want to emphasize that because what Yorgos has done for this project is absolutely amazing. It was a one-man show, right? He did the analytical calculations, he did the simulations, he did the analysis of the simulations, the mock observations, and now he's working with data. So he's really been amazing. He has carried this whole project. And so this is Yorgos. He's very charismatic. It's a pity that I'm here today talking about this and not Yorgos. I will tell you the story. It goes like that. Do you know about the 3-minute thesis competition, right? It's held in many universities. You're supposed to present your thesis in 3 minutes, and whoever does it best wins. okay? And this is done at the university level in all disciplines. So Yorgos, other than astrophysics, he also does theater. You know, he's very much into communication. He's very good at it. So he says, I want to participate. So I tell him, of course, you should do it. That's great. It's a great exercise. You should know you're not going to win because you're a cosmologist. And that's at the university level. You're fighting against people who, you know, are curing cancer. You know, they're doing metamaterials. They, you know, have a scarf and it charges your phone from the sun. You know, they're doing things that everybody can connect with, right? So if you present your work in a general audience, of course, you cannot win against these people. Yours says, okay, I understand, I'll try. So that happens in 2 phases. He does his presentation in the first phase. He does very well, passes in the second phase. Now it's open to the public. We all go there to hear him speak. He's very psyched up. I'm just trying to hold him down. You know, it's the cancer curing people. You know, they're you know, feeding the poor. They're saving the dolphins. It's just you're going to do well, but you're not going to win. Okay, I got it. So we go there. First guy stands up, says, "Hello, my name is, I don't know, Kostas." And these are the 2 Greek names, right? Everybody's either Yorgos or Kostas. So my name is Kostas, and I work on curing cancer. There we go. And today's my birthday. So come on, the cancer curing birthday boy. What can we do, you know, against him? And he does his little show, and then Yorgos stands up. He says, "Hi, I'm Yorgos, and I'm a cosmologist." You know, and then you imagine you have this elastic sheet, and there are people stretching it, and you have a big mass, and you know, things are falling into it, but yet the other people trying to stretch. Everybody suddenly, you know, they're psyched up. Everybody's a cosmologist. You know, the biologist is a cosmologist, and the philosopher is a cosmologist. No, they give him the committee prize. They give him the audience prize. Everybody looking in their pockets for cash to throw at him. He won everything. So there he is, standing there very pleased with his awards and director of the university. Okay, so I'm going to try to do justice to the project, but of course, you know, just you should keep your expectations low. I am not him. All right. So before we go any further, let me fulfill my contractual obligation to flash you with our sponsors' logos. Okay, moving on back to the message. Okay, turnaround density probes cosmology. First part of the talk, insights from a spherical cow. All right, so what does the cow say? The first thing, so what do I mean by spherical cow? Imagine homogeneous universe, completely homogeneous, and in it you have a single, fully spherically symmetric overdensity evolving. Okay, so what's going to happen is it's going to become denser, it's going to collapse, virialize, form a relaxed structure, and then this structure is going to keep accreting matter around it. So that's the physical picture we have in mind. And the wonderful thing is you can solve this analytically. Well, not quite. Once you have some dark energy there, it's semi-analytic. You have to integrate numerically, but still, it's a very well defined problem, and you can learn a lot from it, although obviously the simplifications are very important. Okay, so what does the spherical cow say? So the first thing that the cow informs us about is that the turnaround density, as I was telling you, is universal at a fixed redshift. Doesn't matter what mass the cluster has. It doesn't matter how it got there, if it ate smaller clusters to grow, or if it grew completely through gradual spherical accretion, that doesn't matter. The density on the turnaround scale, all of the matter divided by all of the volume at the turnaround scale, is a fixed number at a fixed redshift. Okay, and here is the cartoon again to keep in mind. Everything that's sort of blue, if you add up that matter and divide by the volume of the blue region, then you get the universal turnaround density. Okay, second thing the spherical cow tells us is that the turnaround density depends on cosmology. And now I am going to show a plot, okay? All right, turnaround density depends on cosmology. What plot am I going to show you to convince you about that? On the x-axis, I have the logarithm of the scale factor, okay, of the universe. So this is today, Okay, scale factor equal to 1. This is the far future, and this is the far past. Okay, so time goes to the right. And on the y-axis, I'm going to show the turnaround density expressed in terms of an omega. Okay, so as fraction of the critical density today that is required to make the universe flat. Okay, so as you have omega matter, omega lambda, this is omega turnaround. Turnaround density divided, normalized to the critical value of the density. Okay, so it's a dimensionless number, and I'm taking its logarithm. Okay, so let's see what happens for various cosmologies. How does that turnaround density evolve with time in various cosmologies? So cosmology number 1, the green cosmology, omega matter equals 1. There is enough matter in the universe to make it flat, and there is no dark energy. For a very long time, when I was young, that was the cosmology. Okay, so I've been through a few. I'm old enough now. We didn't have concordance cosmology. When I was growing up, there was no lambda in the universe. It got invented later. All right, so let's start from there. The good thing is that's a very easy solution. All you have in the universe is matter, and matter evolves with time as a scale factor to the -3, right? You just have particles, and you expand the volume, so the density falls as the size to the -3. All right. So the thing with the turnaround density is that it evolves with time in the same way with the scale factor as the dominant component of the universe at any time. So is matter the dominant component of the universe? Good. The turnaround density is going to change with time as matter. So in that case, as a to the -3 at all times. Right? And that's what it does. All right. Now let's try a different cosmology. Let's try the concordance cosmology. Omega matter equals 0.3, omega lambda equals 0.7. Right? The thing we see in the newspapers.
All
right.
Sorry,
yes.
You can remind me, what is the factor then? It's overdense in the green compared to.
Yes.
What's the classical value that it's overdense? What is about the y-axis value at today?
Okay. So today, the value today, it depends only on omega matter. And I will show, I will have it in another plot. This is logarithmic scale. It's very hard to see, but I will show you one that's not, it's 4, 6, something like that. Okay. So this is, it's around 0, yeah? So order 1 is the
overdense compared to the average.
Yes, yes, it's, well, in concordance cosmology is overdense by 11 today.
11, that's what
yeah, it's delta 11.
Oh.
But not in this one, right? This one's a little bit more than 11 because you have more omega matter. Okay, so it falls like at the -3 in that case, and if there is lambda, things change. In the distant past, lambda wasn't doing much, right? The universe was still matter dominated. So the dominant component of the universe was raw matter, and the turnaround density also evolved as raw matter. In the distant future, the dark energy will have diluted everything else so much that the only thing you will have will be dark energy, okay? And of course, the density of the dark energy does not change. It goes as alpha to the 0, right? So it flattens off the turnaround density. And at late times, the turnaround density also does not change with time. It's a cute result of the spherical collapse model that at late times, the turnaround density becomes exactly twice the density of vacuum energy of the cosmological constant. So you know where it's going. And if you have the red cosmology, which is you have omega matter equals 0.3, like we think is happening in our universe, but no lambda, no cosmological constant, then in the beginning, again, you evolve like matter, because matter dominates in the beginning. At late times, what dominates is curvature, because that is an open universe. And curvature evolves as a to the -2. And so you go from turnaround density goes as a to the -3 to going as a to the -2 at late times. Okay. Now, there are two cute things from that plot. One is if you look closely to what happens today in the universe where we think we live in, that slope of omega turnaround with time is already flatter because we're entering the flattening off period, right? It's already flatter than -2. So if you can measure it very, very well, that slope, you know you have to have lambda. Because if you don't have lambda, the shallower you can be ever is -2. When curvature dominates, if you're in an open universe, that's it. You cannot go closer to 0 than -2. So that already tells you that this should be a very good probe of the presence of dark energy. Okay? If dark energy exists to the extent we think it does today, you should already be able to tell just by comparing the turnaround density today with, say, the turnaround density tomorrow. Of course, if you have magical powers and you can measure the turnaround density tomorrow and the day after tomorrow and, you know, in 10 billion years from now, it will, you know, you can just read off the value of how much cosmological constant you have, right? You just take the turnaround density and divide by 2. So that's a great project. I try to convince funding agencies they don't want to wait 10 billion years. You can't hold their attention for so long. So we have to do something else, okay? And if you cannot look into the future, nobody wants to wait 10 billion years, the other place to look is in the past, okay? Because that's easier. When you look far away, you're looking into the past of the universe. So that's what we should do. Okay. So this is now what I'm going to show is going to be the observer's plot, right? So now time grows to the left, redshift grows to the right. So the further away we look, the more far away clusters will be at higher redshifts. So they will tell us what the turnaround density was in the past. Okay, so again, the 3 cosmologies, green, blue, and red cosmology. Green, I remind you, is omega matter equals 1 over lambda. It starts between 5 and 6 omega turnaround, and it rises very fast as you look back in time. Now, red cosmology starts lower because remember today, omega turnaround today speaks to omega matter today. Okay? So because we have omega matter 0.3 in the open universe without lambda, you start at 4 and then you rise, but you rise more slowly than if you had more matter. And then if you have lambda to the extent we think we do today, you're going to start about the same place because here you mostly depend on omega matter today, and you're going to rise very slowly compared to all the other cases as you go back in time. The reason being you have entered that flattening off region we said before, it's trying to become independent of time. So if you're looking yesterday, the day before yesterday, the day before that, it should grow, but it should grow much more slowly. That's the idea. That's a test, okay? And now the question you should be asking me, and the question we were asking ourselves was, okay, but how sensitive is that? So if I take 100 clusters and I measure their turnaround density at redshift 0.3, how much can I constrain, you know, the difference between different cosmologies, right? So next I'll show you what the constraint looks like for 100 clusters not measured very well. Okay, so numbers are on your side. It's a universal quantity. So if you measure it in many clusters, you get a stronger constraint. So I'll show you 100 at redshift 0.3. Okay, it's a good probe. That's what I'm saying. It's a good probe. All right. So back to the message, turnaround density probes cosmology. You should keep in mind all this is great, but our cow was not very cow-like. Okay, it was a sphere. And so we should let the cow grow limbs. Okay? So realistic clusters look like, you know, an octopus is a better description than a cow, right? It's all the filaments connecting to the cosmic web. A sphere is not a very good description of a cluster. So what happens if you go to cosmological simulations and body simulations, you grow real clusters, and then you try to confirm these results? Okay, I'm going to show a different plot. And now that will be the plot for a realistic cluster. So what do? We take a cluster, and the behavior I'm going to show you is pretty typical. And you find its center, and then you grow spherical shells around it, and then you measure the average radial velocity in every shell. And you plot this as a function of radius of the shell. So here's what a realistic cluster looks like. Okay, this is 0, right? So no radial velocity with respect to the cluster. What's happening here? This is the relaxed part of the cluster. Okay? So you have shells that go up and down from 0, but these are, each individual, say, dark matter particle has a velocity, but they all average out to 0. They're moving pretty fast. The cluster is just sitting there, it's realized. But on average, if you average out everything, it's 0. Then you have this region here where you have negative velocities. That means you have infall. Okay? And here you have negative velocities too, but less and less negative. And then you hit the Hubble flow. Okay? That's the expansion of the universe, systematic positive velocity. So where is turnaround in a realistic cluster? It's right there. As you're coming from outside, doing this averaging, the first time you hit 0 is a turnaround radius. And you have negative velocities.
Is that a little another cluster?
Yeah, that's substructure. Okay. All right. Now, you should not be very impressed by that, because you can always do that for any structure, even if you cannot meaningfully define a unique turnaround rate, right? Because eventually the universe is expanding. As you're coming from outside inwards, eventually you will hit 0 before you have all the nonsense inside. That is not telling you much. It's not telling you, for example, that at the turnaround radius, individual particles all have velocities that are about 0. You could have particles moving very fast inwards, particles moving very fast outwards. It averages to 0, but it's not, a single shell. That's a very good description of reality. So instead of that, I'm going to plot now the average radial velocity. I'm going to take the radial velocity. I'm going to square it for each dark matter particle. And then in a shell, I'm going to take the average of that. So if you have fast velocities, but they all average out to 0, if you take this, it will be a large number. So that's what I expect at the center of the cluster, right? Everything is going very fast, but in random directions. So the average was 0 in that plot, right? In the inner parts, the average is 0. But on that plot, I should expect a high number. And then if at the turnaround shell, everybody's radial velocity is about 0, then you should have a very small average value of the velocity, the radial velocity square. Okay? It does that. They all do that. It's wonderful. So at the center, indeed, you had an average velocity close to 0, but now the average square is very high. But look at how close, not low, how close to actual 0 you are at the turnaround radius. Okay? This is the turnaround radius, and all of the particles in the turnaround radius, they're really, really slowing down. Okay? So indeed, a single shell, a single turnaround shell, a spherical shell, can very well describe that transition between infall and the expansion. And the reason why we're so close to sphericity at these large scales is that it's a dynamical effect. Really, for these guys out there, they see all of the big chunk of mass as a point mass at the center of the cluster. They don't care about if it has substructures, if it has limbs. You're far away from the action. So you're far enough that a single spherical shell can give you useful information.
But is that true if you just take the particles in overdense regions in the shell? Like the ones in the filaments, are they also 0?
This is, well, if you, it's the difference between this and 0, right? So the mass weighted deviations okay, is what makes this not touch zero, but be very close to zero, right? So in the overdense regions, the substructures, right, you will have a small chunk falling in the cluster and crossing the turnaround radius. So you're going to have a little bit of mess there, but it's not large enough to rise that much above zero. It's, as you can see, it's very close to zero for particles. All right, so the real question though, all this is good. It means a turnaround shell exists. The real question is rho turnaround universal in realistic clusters? So now if I take the mass of all dark matter particles, not at the shell, but inside the shell, I add them all up and I divide by the volume of the shell, will I find a specific value of the density? In other words, will I find it to follow this line, which has a slope of whatever it is, m to the minus a third, yeah? Up to the 1/3, okay? Mass being r to the 3. That's a single value of the density. That's one question. And the second question is, the amplitude of that line, is it where the spherical collapse model tells you it should be? Okay, so that line both has the correct slope, but also it has the normalization, the spherical curve prediction. All right, so now let's see a lot of clusters. Before I was showing you one, so you might say, oh, it's your favorite child. You just found one that looks good. Now I'll show you a whole bunch of them. Okay, so it exists. That good property is retained. So there's only one thing left to ask. And this is, okay, this is at redshift 0. If you go backwards in redshifts, if you take that universal value of the turnaround density and you look at it as a function of redshift at different cosmologies, will it do what you think it's doing, right? Can it probe cosmology? So does rho turnaround probe cosmology in simulations? And the answer is a very strong yes, okay? So these three lines are concordance lambda CDM, so omega matter 0.3, omega lambda 0.7. This is, red line is omega matter 0.3 and no lambda. And this purple line is omega matter equals 1, no lambda. The solid lines are what spherical collapse tells you it should happen. And the points are clusters in full embodied simulations. So they do exactly what you think they should be doing. And so if you measure these points with groups of clusters at different redshifts, you should be able to tell between these three lines. So you should be able to probe the contents of the universe in that way. All right, so back to message. Turnaround density probes cosmology. And for that reason, we should observe it, right? Okay. This is where everybody is along for the ride. If I give this talk to cosmologists, usually this is where the first objections come up. And they are of the following kind. Do we really need another probe? I mean, don't you already know that omega lambda is 0.7? Why are you even bringing this up? You know, why are you rocking the boat? You know, we know omega lambda is 0.7, we know omega matter is 0.3, that's behind us, and let's talk about tensions now. I want to talk about the Hubble constant, not about omega. So do we really need another probe? Let me try to answer that question by doing the litany of the 6 virtues of the turnaround density as a cosmological probe. Virtue number 1, it has different systematics than everybody else. Okay, this is a talk among friends, so I'm going to say it. There is no supernova physics involved in this probe. Okay, so why do I care about supernova physics? All right, so that's hear me out. Okay, all right. Omega matter, omega lambda plot, right? The constraints of the contents of the universe. There's 3 lines we plot there. One is the line of the CMB that tells you omega matter plus omega lambda equals 1. Okay, it tells us the universe is flat. 1 is the measurement of the contents of the universe. You do baryon-acoustic oscillations, or you measure the mass of clusters, and they tell you omega matter equals 0.3. Okay, and these two just meet at omega lambda 0.7. Now imagine that you are not allowed to have the supernova line that we are told passes exactly through the point where the other two lines touch. And the reason for that is that because you cannot make really the assumption that supernovae are calibratable standard candles all the way to redshift 1. To put in other words, imagine you have just a little bit of evolution of supernova properties, say with metallicity. Okay, so I take the supernova line away. You cannot have it. You cannot claim supernova acceleration anymore. Do you now believe there is omega lambda? And the reason why I'm asking this is the other two constraints, we had them for a very long time before the supernova. We knew omega matter was 0.3, and we knew the universe was flat. And what that did to the cosmological community, you had two camps saying, no, omega matter cannot be 0.3 because I know the universe is flat. There is more matter and you're missing it. And the other group was saying, I looked really hard, that matter is not there, the universe is open, your CMB measurements have some systematic. No, but at no point was, and you know what? We have 70% dark energy, a viable solution to this fight. It was only when the supernovae came that we said, okay, it looks like it's accelerating. That's it's weird. I don't feel good about it, but this is what must be happening. So, and that's why every few years you get a group saying, look, I looked at the supernovae and there might be a little bit of evolution of supernova properties with metallicity, and then it's a big deal. Okay, so if we had a probe that does not speak to supernova systematics at all, we can put this to rest. Whatever it finds, it doesn't matter. Yes, lambda, no lambda, doesn't matter. Okay, it's a good thing. All right. So it's the other thing. It probes dark energy on cluster scales. You look at that cluster, and you say, look, in these 5-6 megaparsecs, there has to be dark energy because it's messing with the turnaround density. It's not a universal quantity for the whole, universe affecting the acceleration of the universe as a whole, right? In gigaparsec scales. Now you are.
You can basically get every single word that you say in the next office. Would it be possible?
Of course. Yes.
Thank you very much.
You can join us. Okay. All right. So cluster probes. So it's a probe that happens on cluster scales, right? So it's you lose, say, the need for a factor of 1,000 in size to probe dark energy. So it's a box of dark energy and you can see it. And that's the very first time you can do that. It's very cool. All right. And the third one is, if you remember how fast it grows apart with the other cosmologies, it happens in the local universe. It happens when you compare redshift 0 to redshift 0.1. You don't need to go to redshift 1, redshift 2, redshift 3, like you need with supernova to see it happening. Okay, so it really probes dark energy today. And of course, you could do the same thing by comparing redshift 0.3 with redshift 0.4, redshift 0.8 with redshift 0.9. What does this do? It tells you if dark energy evolves with time. Okay, so it's a great probe of the equation of state, dark energy, whether it's a cosmological constant not evolving in time, or whether it is some sort of field that really has an equation of state, a W that's not -1. Okay, but these 3, and I promised you 6. Fine. So number 4 is I'm telling you to measure clusters, okay? It's not like I'm telling you to measure supernovae that are transient and you have to chase them and you have to be lucky. You can schedule your observations. Clusters are just sitting there. They're good targets. Right? They're very friendly. It's just, where the cluster is, you go when it's a good opportunity and you observe it. You don't have to chase after transient, and you're observing them anyhow. Okay, they're workhorses of cosmology. You have been observing clusters for 20 years. Probably if you just take the data and analyze them with a different look, you're going to gain all these constraints on the contents of the universe. All right, and number 6 you're measuring a universal quantity. So everything that anybody has told you about, for example, mass functions, we do them in all different kinds of astrophysics research. And you have to be very careful about your quality cuts and your completeness criteria and the biases that enter through completeness criteria. So doesn't matter. You're measuring a universal quantity. Just pick the good clusters. Pick the ones that are not in the process of merging. Pick the ones that look more spherical than others. Pick the ones that are in the part of the sky you were observing anyhow. Pick the ones that from a good family, whatever you want. Doesn't matter. As long as your quality cut is not the ones that have the turnaround density that I want, it doesn't matter because you're measuring a universal quantity. Yeah. Okay. All right. So what would it look like? Let's say you got convinced, you go out there, you measure all the clusters you can find. So by that, I mean the 42,000 Sloan Digital Sky Survey galaxy clusters at redshift smaller than 0.3. So what kind of constraints did you put on that plot? And this is what the other constraints look like, right? CMB, Planck, baryon acoustic oscillations, and the fat supernova line. Supernovae are a line, and it's a pretty fat one. Okay, so here's turnaround density. I haven't done it, right? This is not a real constraint. It's a projection. What I think will happen if, well, right? So once we learn how to do this, and we do it well, and it's as mature as all the other probes, it's going to be an extremely strong constraint. And please note, this is a point. It's not a line. It probes both the matter density, because the turnaround density today speaks to the matter density, and it probes the dark energy density, because the way the turnaround density evolves with time probes the presence of dark energy, and that's it. Okay, you just measure this one thing, and you get both parameters for free. So it's really cool. All right, almost done. Okay, so remember, the message of the talk is turnaround density probes cosmology. And I'll just leave you with some thoughts about observability, which is, if I don't do that, the first question is going to be, can you observe? Right. So I want to say that people have been observing the turnaround radius. It's not science fiction. And they have been doing it before realizing that the turnaround density can give you cosmology for nearby clusters. Okay? So one way you can do it is by looking at through the center of the cluster, line of sight velocities, and then here is 0 with respect to the center of the cluster, and here is a Hubble flow at large distances. And so you observe redshifts, and this is where that curve crosses 0, and this is a turnaround radius. Now the trick is, how do you order the galaxies on that axis? You need some measure of their distance, which is not the redshift, right? Because the redshift is the other axis. Okay? And this for nearby clusters, you can have in many ways. You can have supernovae, you can have Talley-Fisher relationship, you can have red giant branch galaxies, and whatever. And if you can do that, then you can measure the turnaround radius. And here it is for Virgo also. Same technique. Right. The problem is this is not scalable. Right? You can do it for nearby clusters, but the cluster point redshift 0.3, how do you measure independently distances for 1,000 galaxies? For 100 galaxies? You cannot wait until a supernova type 1a goes off in each one. And I told you I don't want to use supernovae, right? That was how I advertised it. So you need something more general. Okay. So this is fresh off the, not even of the press. Yeah. In a couple of months, it's going to be in a preprint server near you, different papers. Okay. So what do you want to measure? You want to measure a density, a turnaround density. And that involves measuring a mass inside the turnaround radius, and the turnaround radius. Okay. So how do you measure the mass? Well, it scales with M200 in a very predictable way, and for a very well understood reason. It has to do with how the profile of the matter goes once you're outside the turnaround. So once you are outside the relaxed part of the cluster, then it's very easily calculable how matter will structure itself around the center. And then how do you measure turnaround density? Well, the turnaround is a kinematic effect, right? Things are going outwards, outside, and things are accelerating inwards, inside. So it imprints in the mass and galaxy profile. So you can measure it on the plane of the sky, quasi straightforwardly for a lot of clusters. So the road is open, and we're hoping in the next few years, we're going to have a measurement, and we're going to have more to talk about in cosmology with this new tool. Thank you.